So this is an extended version of a talk I gave at the Flight Software Workshop 2024 in San Antonio. It is meant to be kind of like an introduction and an perking of interest for Erlang-based technologies for non-Erlang users, focusing on Erlang's fault tolerance. So this was given to flight software engineers who usually don't work in Erlang, at least not that I'm aware of. But if you stumble upon the video, so this is meant for everyone who is interested in the technology and see what it's about. Okay. So first, a little bit about the blob paradox. So that there's a paradox that when we learn different languages, we know that the languages are sorted in some kind of order of powerfulness. Because if that would not be, we would all be programming in assembler. But nobody, or at least not many people, want to work in assembler anymore. So they rather like to use a more high-level language, like C or C++, or even more high language than, let's say, Python or Lisp or Erlang. And the paradox is that while basically from the level of language one knows, one clearly sees that the languages below it are missing very important features, which we can't understand how we can actually live without with anymore. But in the other direction, kind of like the features that make the languages more powerful look bizarre and unnecessary. So kind of like everything looks at the same level. So this is just a weird language, not a better language. But as soon as we learn it, we find out, oh, this is actually better than before, and it gives me more power. This has been discussed at length in the article of Paul Graham, Beating the Averages. Very recommended reading. The link is in the slide, and I will share the slides also with together with the video in the end. So, kind of like after opening our mind to actually see how to look upward, because I think Erlang is pretty much one of the apex predators here in the programming language world. Paul Graham used Lisp as an example, why Lisp gave him and his partner superior power, actually implementing the first user configurable web shop and selling it to Yahoo. I really strong belief that basically Erlang is even above Lisp. So even beyond the language that he describes, because it has everything Lisp has, but many, many things more. It's not so focused on macros like Lisp, but I think that's a mixed blessing anyway. So what does Erlang give us? It gives us transparent distributed programming. I put that first because that was the feature that actually attracted myself to the language. Many years ago, I needed to build a distributed version of an existing system, and Erlang had this transparent distribution. What does it mean? If I'm talking to a process on another node, I don't see any difference to talking to a process on my own node. So it makes distribution or different nodes or different computers in your network as transparent as possible. Of course, latency you can't hide, so there will be higher latency if you talk to a different node, which, well, you can't hide that because the universe doesn't let you. Latency is because of light speed, and light speed is a thing that's seemingly non-negotiable. But then the main reason I stayed with Erlang is its failure tolerance. So what does it mean? It means your program has a bug and it keeps running. And we will get much more details about that, how and why that is working, because that needs more information to actually support this claim, because the claim sounds almost impossible, magical. Like, how can a program fix itself and keep running? It's also soft real-time. That was an important property that was necessary for the initial space that Erlang was developed for telco systems. So, I mean, the philosophical question is, what does soft real-time actually mean? We all know about hard real-time. Well, maybe we don't, but there's hard real-time and soft real-time and no real-time. But the whole real-timeness is on a spectrum anyway, because even hard real-time is not 100%. Hard real-time usually misses, it's an error when you miss a deadline, but you can still miss a deadline. Let's say the computer breaks, and you missed your deadline. So it's nothing is 100% or a power outage, miss a deadline. And if you duplicate computers and multiply redundancy, you only can push the probabilities anyway. So soft real-time basically means that the probabilities are a little bit skewed more into the non-real-timeness, but are pretty real-time, usually. And that is actually good enough for many applications that need some real-timeness, and much better than no real-timeness, usually, because it totally avoids these very long pauses that, for example, garbage collected languages like Java impose on you when it needs to do a stop the world garbage collection, and other reasons that systems are not real time. Kind of like as a side effect, because that was not what it was designed for, it has an insane level of concurrency, which actually gave it a lot of scalability on SMP, which kind of like caused a little hype cycle around 2010, because that's when SMP was kind of like taking over the server market, and nobody knew what to do with their multiple cores. Most of the programs were only able to kind of like saturate 1 or 2 cores, and it has shown to be very hard to actually get more cores. And also that multi-threading is not a very good model to actually program that, because it's very error prone. And even if you do everything right, the synchronization, the necessary synchronization, breaks the level of concurrency and parallelism that you can achieve. If you want to know why, look up Amdahl's law. That tells you how much sequential code you are allowed to actually have a lot of concurrency. So that was kind of a side effect, because Erlang had no problem at all to saturate a 128 core machine with an application that was written in a very natural way in Erlang, like a normal machine, normal application, not anything very, very special developed. In the meantime, kind of like this space has been taken over by microservices, and I also have a few words on those later on. So the workaround is here, since we kind of like are not very good at programming multi-threaded programs in most of programming languages, we kind of like are starting programs in processes or in containers at the same time, and basically this uses up the available compute power. Unfortunately, it actually uses up a lot of compute power just for the overhead, which you can avoid with Erlang, and that's why you get this huge scalability, which made it a choice of technology that was actually crucial to make companies like WhatsApp, so by the way, WhatsApp is written in Erlang, highly successful. It also gives you higher productivity, lower time to market. That's also kind of like a claim that needs some substantiation, but it's much harder to grasp than the other properties. But I try to give you a few examples of that. So what else do we get? It's a safe functional language. So it is safe in the sense that you cannot have like arbitrary memory accesses. You use of the free allocated memory. It's dynamically typed, but it actually has strict dynamic typing, which is a difference to, for example, languages like Java. not Java. Java is actually statically typed. I mean JavaScript, because JavaScript has all these automatic conversions between different types, and that means it's not strictly typed because of these automatic type conversions. So Erlang doesn't do that. So any runtime type stays the runtime type until you explicitly do something with it, and do some computation with it, and it never changes, basically. We have optional type checking, so there is actually a bunch of type checkers. In the meantime, there used to be dialyzer, which comes with the system, but there's a whole plethora of other type checkers using different type systems and type inference. And there's also a type annotation language, which is part of the language, and which can be used to actually give information to the type checkers. So it's kind of like it can give you good things of both worlds. You can work in a dynamically typed language, which gives you high productivity to actually evolve the program quickly. But then when the program settles down, you can actually crank up the type checking, and that gives you the best of both worlds. It has immutable data. So what does this mean? So what I do here is I just start the shell, and that actually shows you another reason for higher productivity, because it actually has a read eval print loop, and you can play with your code and with your systems in an interactive way, which actually is very helpful to evolve your programs. By the way, maybe I explain the thing. So we have Erlang OTP 26. The current version is 27, but that's just out. So I'm still on one version behind. That's the version of the runtime system. I don't even know what that is. I'm on a 64-bit system. It's running SMP on 16 cores. My machine has 16 cores. And apparently there's no hyper-threading because that's hyper and real threads. Or do we have 16 real and 16 hyper? I don't know, sure. And that's kind of like, that's other schedulers here. So that's the number of schedulers, because Erlang has these very lightweight processes, and which are much more lightweight than a thread even, but behave like an operating system process. And these schedulers actually are then responsible for very efficiently scheduling these things. So what, I mean, it's very hard to show you immutable data, but one thing is basically it's, you have single assignment. So you can do basically, if I say X or uppercase letter is a variable, and I say X is 15, and then afterwards I want to say, oh, now X is 13, or let's do something more usual in other programming languages, X equals X plus 1, then you see that's not possible. You can't change X when it has a value. So that sounds weird, but normally we have no global variables. So this is just a variable in the shell process. So every variable is only valid in a function. And usually we have very small functions, and every variable name can only have one value. Funnily, I can actually do that again. So X equals 15 again, because when X is already bound, this is pattern matching. So the equal sign is either binding a variable on the left side or pattern matching, or actually to be clearly true is it is both. It uses pattern matching to bind a variable. So so we saw one data type already, that's numbers, 15, and of course you also can have floating point numbers. I always need the full stop to kind of like end the statement for the shell. And as of kind of like more constructed data, the simple ones is we can have tuples, which can have a mix of, that's full, 15, and 4.5. So that's a tuple of 4 elements in the braces, with first element is an integer, with the number 1. The second one is an atom, a symbol, basically named foo. So it has these symbolic atoms and all the other numbers. So basically it gives back the thing to me, and I can actually pattern match with that. I can do A, comma B, comma 15, comma C. So I expect now on the right side of the pattern match a tuple
which has exactly 15 at the third point, and we don't care about the values in the other thing, but since A, B, and C are variables which are not assigned yet, they will be then bound to these values. So I copy that, just not to confuse people. So that matches because the third one is a 15. And now if I look at what A has its value and B has its value, so actually we pattern matched out all these values. And that is a much more powerful paradigm that it looks in the beginning, because this pattern matching goes pretty deep. So let's say we have a complicated, no, X is already bound. So let's use Y. We have a complicated thing. So we can also have lists. So this is the square bracket actually starts a list. And let's say the list actually has a first thing, which is a tuple, okay, 15, and the second element is 16 and ABC. So we can also have a mix, but the list is actually kind of like not of a fixed length, so it can be more easily extended. The tuple always stays the same length. Of course, you can assign the values to other tuples, but the list can be extended. So I show you how that works. So now we have this list. And for example, you can also construct lists by Z equals by kind of like this operator. If you're coming from list, this is a cons operator. So I prepend something. So I prepend, okay, 10, for example, a tuple, and put the rest of the list here. And then we have basically prepended that to the list. If you now want to pattern match, we can actually also use the same operator to pattern match. So we can, for example, say on the left side, I'm expecting a list with the first element a tuple, with the first the atom okay. And then I'm actually interested in this value. Now I need to see which letters I didn't use. Let's say E. And then the rest of the list. Also pattern match to the whole thing. And we now pattern match that to C. So that was the original list. So that matched. Now we look at what we have in our values. So in E, we have 10. So that we pattern matched out this 10 here. And in R, we have the rest of the list. So that's how you deconstruct a list with pattern matching. And you can go arbitrarily deep. And also this pattern matching is used for one feature of the fault tolerance, because we want to detect corrupt state very early on. And because usually you use pattern matching, so stating your assumption about the structure of your data that you have. So it's almost kind of like a runtime type check in a structural way at every line. So if you would be programming C, this would be like every line of Erlang code is usually corresponding to a line of C code with a bunch of assertions in front of it. And these pattern matches also can have guards, so you can actually say pattern match this when this extra condition about the pattern is true. I think that goes too far to actually show you that. So let's have a look at our slides again. So mutative data train nothing model, that is pattern matching. We were here. Pattern matching, including binary bit string pattern matching. So let me show you binary bit string pattern matching, because so Erlang has a binary data type. So that's basically an assortment of bytes or bits, can actually be odd numbered. So let's make 5 bytes with the numbers 1 to 5. So that's a binary blob, a buffer. And then you can actually do pattern matching like that. I say the first X, the first 10 bits, and then no, I can't use X because I already bound X. I think I need a new shell soon. And the final, whatever. Let's see if that works. I'm using a trick here in the shell. Y -1 is basically the value of the last line. And that actually doesn't match why we get these dots here. I think I introduced a syntax error somehow. Yeah, but it seemed to have worked now. Let's see what F looks like. So F is now 4. So we actually did a 10-bit match on the left. So we can actually really bit match out bit patterns here. We did a 10-bit match. So that is like the first byte is like 00007 zeros and a 1. And then we actually match 2 more. So it's 100, and that's 4. And D would be a bit string. And there you see basically this is only 6 bits in there, and so you can have odd bits there. I think that's enough of a demo. So let's go back to the slides.
That the variable doesn't change. That's kind of like a prerequisite for the variable not changing. But if you actually have a list of elements, you can't change the values in the list. So whenever you change something, you make a copy of the initial thing. And with lists, often you change something in the beginning. And because the data is immutable, you can keep basically it implicit keeps the pointer to the rest of the list because it can never change in the future. So we are actually we can do certain optimizations because of this immutable data, and don't need to copy all the time. So that's one thing. The share nothing model is very important. So we have these processes, which is the smallest unit of execution. So we didn't see the processes yet, except that the shell prompt, this is a shell process. So there's one process running the shell. A little bit more about processes later on. The most important thing is they don't share their heaps, so they don't share the memory. There is no shared memory concept. Well, that we have one shared memory concept, but that's a separate story. But not shared memory per se. It's a shared table of values that you can actually use as an optimization. But normal processes only share or only communicate by sending each other messages, which is part of the fault tolerance story. Because the important thing is that the corrupt state gets actually contained and can't escape. It also supports hot code upgrades, because if you want to have a fault tolerant, why did you want the fault tolerance in the first place? Fault tolerance you want because you get systems that run forever without being interrupted. And but if your code upgrade requires the system to restart all the time, then every small upgrade, you have a lot of interruptions due to this upgrade. So as soon as you have fault tolerance, you also want no disruptions because of upgrades. So Erlang supports hot code upgrades, and it goes from a single module. That's something that we will be actually doing later on in the final demo. And then it also has infrastructure to update a whole system, where you need to take care of like updating this thing in the right order, or if certain processes communicate a lot, you might want to suspend these two processes and then upgrade them. And so there's a whole kind of like infrastructure for code upgrades there. So that's why the picture for, yes, we can change the tires while we keep driving, basically. Pattern matching, we just saw something, and because of a few of the things, especially concurrency, like you can actually express everything that's actually supposed to be concurrent in a concurrent way. You don't need to kind of like force yourself into weird models of concurrency. Like if you want your layers of a protocol stack being running independently, talking to other layers only, you can actually implement it like that. You don't have to do tricks to achieve that. And because of the pattern matching, especially binary pattern matching, it's actually perfect for protocol implementations of all kinds of protocols, more like text-based protocols and also binary protocols. I personally have implemented a lot of protocols. We had a legacy product which was in the automotive space, where they use a lot of very interesting protocols to talk between control units each other, and they have a whole series of protocols and versions. And I implemented all of them single-handedly in Erlang, and that was only possible with one developer because it gives you superpowers for implementing protocols. So this shared nothing model, kind of like in safe systems, this gives you the space partitioning already. So every process is space partitioned. They not in a security wise, but in a safety wise. So if you can't touch the memory of another process. So more about processes. These processes are super lightweight. So on I think that was on a 32-bit machine, it's 300 bytes per running process memory, and I think on a 64-bit machine, it's 600 bytes per running process for obvious reasons, longer word length. So that means that you can have lots of processes. It's not a problem to kind of like spawn 10 million processes in an Erlang node running on my laptop. If that helps you implement your system, that is what you can do. There's not much cost associated to a process. So we in the Erlang languages, basically, so in all languages based on the Erlang VM, because there's several. But today I'm mainly talking about Erlang. We use processes like objects. So there's no further cost. Like some objects are much more heavier than an Erlang process. Between the processes, we have asynchronous message parsing. The message parsing is transparent in a distributed way. So the processes can be on different Erlang nodes. There's extra features about process linking and monitoring. So that's an important feature for the fault tolerance and for a few other features. I first say short thing about linking. You can link two processes together, and that means when one of these two processes crashes, the other one gets an exit signal, which is a special message, which you can catch it. You can trap exit signals, then you can handle it. Or if you don't handle it, you crash with the other process. So an exit signal exits your process. So if you have two processes that communicate a lot and work closely together, you like to link them together. And then when any of them breaks, the other one goes too. And then what you then do, we see on later slides. Monitoring is a different one. So process linking is actually inherently bidirectional. So there's no direction to it. And two processes are linked and you link them again, there's no stacking. They stay linked. That's now. If you unlink them, then there's only one unlink. But usually don't unlink. It's very rare. There's another thing, because what you need is sometimes you want to watch another process and just get a message when something happens with the other process. And you also want to be able to stack that, so to monitor it several times. I explain that in a moment. Which is a more lightweight and it's unidirectional. So the other processes, if the process that monitors another process dies, nothing happens to the other process. It wouldn't even notice unless it monitors back. Monitoring is mainly used if you have a server and you have a request response thing. What you do is basically, before you send your request message, you monitor the other process. So while you're waiting for a response, let's say with a timeout of 5 seconds, and immediately when you send the message, this causes the other process to crash because it has a bug. Then with monitoring, you immediately get informed that the other process is gone and you don't have to wait for the 5 seconds. And because this can be happening in nested function calls, that the same process get monitored and monitored again, you need to have it stackable. So you monitor and unmonitor in kind of like respective pairs. So there's a handle associated with the monitoring. Very important for the soft real time. It has a garbage collector memory model. It has a generational garbage collector, fairly fancy one, copying garbage collector. But these garbage collection happens per process. So these processes have very little memory usually. So it's usually a code smell if you have a process with a huge state in its memory. If you keep your processes small, that means the garbage collection is very quick because there's not much to copy. There's not much live data. So it's very quickly copied. That is a very crucial part of Erlang soft real time. Also, you never stop the world. You only garbage collect one process. So every other process stays runnable and can do stuff. Only this one process is kind of like disrupted for a short moment. Also, very often you do never a garbage collection because processes are also cheap and also very quick to spawn. When you need to do some work done and want to keep going with what you're doing and then collect the results later, you quickly spawn a worker process, and often you have a good estimate of how much memory this process will need. And at spawn, you tell it to actually allocate enough memory right away, because you can give it the initial heap. So the heap grows every time it runs out of memory, it grows kind of like in an exponential way. So the heap gets, I think, with 1.3 or 1.5 factor larger. But you can actually tell it like, I have a hunch, start with like a 5 kilobyte heap, because you will need 5 kilobyte of memory for this computation. And then when the process is finished, it sends back its result and dies, gives up basically, or exits. That means it's never garbage collected because you just use your memory, and it never reaches the point where it runs out of memory, because the lifetime is shorter than the garbage collection. So much for processes. Very important feature in Erlang. Very briefly, there is a very rich library of interesting things. It's called OTP. It was initially named Open Telephony Platform, but since Erlang escaped the telephony world like many decades ago, it actually has no meaning anymore. It's OTP. We just call it OTP, and ignore the initial meaning. That sometimes happens. You name things and then it sticks. So the full system is Erlang OTP because you have the Erlang runtime and the Erlang compiler and the pretty extensive library that gives you things like behaviors. I'll show you behaviors, how they look very quickly. The behavior is kind of like a boilerplate template for a user module to actually have to specify certain or have to implement certain callback functions, which then lets you have all the concurrency and all the gnarly stuff hidden in a shared implementation. And that's, for example, the case for GenServer and GenStatem, which is a generic server. So all the monitoring the other node and make sure that the answer is actually the one that you actually gave it with the response, and a lot of other things that need to be book kept and extra features. You hide that in one implementation of the GenServer, and the only thing that the user implements is a behavior, which is just a set of callback functions, which are then purely functional again, which also makes it much more easy to reason about your code. And GenStatem is a generic state machine. Then there's a lot of protocols already implemented in OTP, because it's not just a library. It's kind of like, because the process is everywhere, it's like applications, which are library code plus so-called supervision tree. We will see that later on, which you can start independently. And so it actually looks more like an operating system from within, because you have applications that you can start and stop. You have processes, you have I/O systems, etc., etc. So it's kind of like, looks like a small operating system within the operating system. It also has a transactional database built in, an in-memory database, which gives you the advantage that you have like sub-microsecond latency talking to the database, and not millisecond latency if you want to talk to an external database. And it also has a distributed mode and is often a good choice. Unfortunately, often ignored because it's not so known for if you need a quick database or a quick distributed database in your Erlang node. Erlang is still maintained. It's actually basically the initial Spark actually started in the 80s. It kind of like consolidated in the early 90s. And then there has been a growing team of developers that actually is building Erlang and OTP and maintaining and extending it and improving things. And since I'm part of the community like 2007, there has been always a team of like 15 or more developers in the Ericsson OTP team. So Ericsson invented the language. And by the way, Erlang is not named the Ericsson language. It's actually named after a Danish mathematician, Agnar Krarup Erlang, who invented who found the most important statistical formula for telecommunication systems. But I guess some of the managers in Ericsson back then in the day, they thought it's called Erlang because Ericsson language. So they're constantly developing it, but it's open source. It's Apache 2 licensed. They do very responsible release engineering. They deprecate features very early on. So it's very industrial process of software engineering. And features are added cautiously and not quickly, so we're not getting flooded by new features all the time in a changing language. Like in some other languages, especially such with a huge open source community, they usually have a higher pressure of the community wanting features. And they also continuously optimize the runtime system, so it's getting better and better, which means that everybody's Erlang code is getting better and better all the time, which is kind of nice to have. There's also a community organization, the Erlang Ecosystem Foundation, since 2019, I think. Personally, I'm sitting on the board. I was a co-founder of it. It's kind of like modeled after the Python Foundation. We looked at their bylaws. It's kind of like membership is personal. Like people are members. Companies can be only sponsors, so they can give money, but they don't control the organization. And then the main reason for its existence is to grow the ecosystem and to organize a space for working groups, including an embedded working group, which is kind of like important to the subset of people this talk is partially meant for. And it also funds a lot of projects for improving things, for the things that kind of like Ericsson is not interested in, but the community wants. And there we actually have a way to kind of like collect monies from sponsors and then fund projects there. So altogether, a pretty good ecosystem. Actually, a very nice ecosystem. It's not a big ecosystem, so people know each other, which is an advantage also. But it's a very friendly ecosystem, and which is probably one of the reasons of its size. If it's smaller, it's more familiar. You know people, you meet each other again, so people are more nicer to each other, and so that is actually a big strength. So now, let me take a sip of tea. Now let's get into this failure tolerance, that big claim that, okay, your program has bugs, but it keeps running anyway. So yeah, everybody probably was on one of these support phone calls where they ask you to switch off and on your computer to fix a problem with your system, and of course you're reluctant to do that. But very often fixes the problem. And why is it working actually? So the thing is, what happens very often systems fail, they have corrupt state now. So the state got corrupted, which means it's the bits in the memory are in a state that the programmer didn't expect them to ever be, basically. It's in a this can't happen state. And the only way to kind of like get it back working again is to get rid of the corrupt state and start with a clean state again. And then you can keep functioning. And that's why switching off and on the computer works. And that's why embedded systems people have a watchdog timer in their systems, which you occasionally need to kind of like give a live sign to that you're still kind of like your system is still up and running. And if it's stuck somewhere, then the watchdog kind of like reboots the whole system. So we all kind of like in embedded space, we know these functions. But this is all the whole system, and that is very coarse-grained. And even kind of like if you look at like what Kubernetes is doing, it's restarting only whole microservices, which are big chunks of the system. So let's look how Erlang is doing that. You probably can imagine already that it is using its very lightweight processes as the smallest unit to restart. And let's have a look at how this works. So there's one of our mottos, which is actually causing a lot of misunderstandings if we use it with non-Erlang users or management. Let it crash. So we actually achieve robustness by letting things crash. The thing behind that is, if the state of one process gets corrupt by whatever means, it is important to get rid of the corrupt state as quickly as possible. Because you want to avoid that the corrupt state can spread to other processes via messages that you send it to, and cause more errors and problems everywhere, because then the problem rises. So if the state is corrupt, you need to get rid of it quickly. And the way you do that is you let this process crash, because one of the most important findings when Erlang was invented is that it is impossible to fix corrupt state from within the same corrupt state. And that's why exception handling doesn't really work the way it is expected to work always. Because if the state got corrupt outside of the frame of the exception, basically, I mean, if you do very clean functional programming, exception handling can do partially the similar things. But if you have some kind of state that is kept around in a process, for example, then you can't get rid of it by exception handling. It stays corrupt, and then you crash again, and you don't fix anything. So let it crash is one of the important things. Very often misunderstood because they're kind of like, yeah, they're failure tolerant, but they crash all the time. How is that going to work? So yes, you crash to get rid of corrupt state. We have a share nothing architecture, so we actually have encapsulation of this corrupt state in small units, where we have very clear patterns of communication outside of these small units via message passing, which lets you control where the state can actually escape to. And if you crash quickly, maybe it doesn't escape, and then you win. And so if you can't fix the corrupt state from within the same context, you need to actually deal with it from an outside context. So you need another process that watches your process, and then takes care of the corrupt state. And these processes are kind of like, there's one implementation of that coming with the standard library. These are called supervisors, because their only kind of like task is to supervise other processes. And like in the initial system start, it starts all the processes, then it supervises them, and it also shuts them down when you want to switch it off again. And so, but still, kind of like the claim is pretty high. Why does this restarting actually work? And this goes actually back to very old research from 1985. Jim Gray at Tandem Computer, who already back in the day knew that you need two computers to actually have a fault-tolerant system. He wrote a paper in 1985 where they actually looked at why do systems fail in production. And what they called, basically, they found two kinds of bugs. One they named Heisenbugs after Heisenberg, the quantum physicist, and the other one Bohr bugs after Niels Bohr, another quantum physicist, which had two models. Heisenberg was basically saying everything is uncertain and you can't know things, and Bohr kind of like started with the Bohr's atom model first, which is more deterministic. So this is about kind of like nicknames for deterministic and non-deterministic bugs, or deterministic and transient bugs. More on these kind of bugs later and why that works. But first, let's start with a concrete example of a supervisor. So the blue box is actually a supervisor here, this one. And the green boxes are its children processes. So we call those children, and that's the parent, because that's a tree. And the gray lines is actually that these processes are linked. So this is a bidirectional link, because it's also important, should the supervisor crash, we actually don't want the children to be orphaned and float around in the system without a parent. The children should go away also should the supervisor crash. And when it would crash, we will see soon enough. So you have this bidirectionally, but the supervisor actually traps the exit signals. So it actually has a special flag on that basically don't crash me when one of my children crashes, but send me a message, and then I deal with it. And this one is configured, so the supervisor basically only gets configured. There's nothing to program there. This one is configured as a 1-for-1 supervisor. That means that when one process crashes, I have this labels, I forgot about this animation. Supervisor child process. So anybody looking at the slides also know what the blobs means. So when one of these processes crashes like this one, the exit signal gets sent to the supervisor. The supervisor gets this message, handles it, and restarts this process. So that is a good thing for isolated processes which don't talk between each other. If any one of them gets corrupt state, you get rid of the corrupt state by crashing it and restarting it with a clean slate. I'll show you another one that's an all-for-one supervisor. So assuming these 4 processes are very interdependent, they send messages between each other all the time, and they depend on each other very much. So if any of those crash, the others, we can't know what state they are in, and it's kind of like it's a lost cause to figure out what's going on. So we have an all-for-one supervisor. So if any children crashes, the supervisor kills all others, sends an exit signal, by the way, in reverse order, and then starts all of them again from scratch and gets a clean slate of this subsystem. And then there's also, for completeness sake, a rest for one supervisor. So let's assume the green blobs are kind of like working in a pipeline. So this one is doing some computation, sends the result to this one, doing something with it, and sends the results to this one. So there's only a one-way communication going on between these processes. So if this one crashes, it can't affect this one. There's no way that this one can affect this one. Then it's actually sufficient to actually restart the ones that come after the corrupt one. So that looks like that. You can imagine how it looks. The supervisor kills the ones that come after the one that crashed, and then they get restarted again. And now we look why supervisors might be crashing. So this normally you don't have only one supervisor in a more complex system. That would be very simple programs, but you have a whole hierarchy of supervisors that kind of like reflect the main design architecture of your system. So if I look at a new Erlang application, if I look at the code, the first thing that we usually look at is the supervisor tree, because it tells us how are things connected. And that is a thing, that is an art form to kind of like learn how to design these trees, because you need to think about like, where is my corrupt state? Where are the error kernels of the system? Like what's the containment of errors in the system, and what state? And you also need to think a lot about state. You need to think, because everybody probably thinks now, but if you just lose your state, then it's lost. And maybe there was something in this state that I want to hold on, which I want to persist. And this kind of like this volatile state in these processes makes you think more about your state, because the persistent state is actually quite dangerous, because persistent state would mean that you can also persist corruptness of state. So you want to minimize your persistent state as much as possible. So persist as little as possible, and think about that. What parts of the state you persist, and everything that can be recreated, like recomputed, you don't persist, because that's only an optimization. So you rather recompute it from scratch when you need to restart. So, but back to maximum restart frequency. So what happens if actually my intervention actually doesn't fix the problem? So let's assume this one, so we're looking at this supervisor here, is a 1-for-1 supervisor, and we have this one, this process repeatedly crashing. So basically we restart it and it crashes again. We restart it again, it crashes again. And now every supervisor has there's a configuration, which is the maximum restart frequency, which you can tell basically if this supervisor has to restart any of his children more than X amounts in Y time, and you can specify both values, then actually a supervisor gives up and kills itself, and hands control over to basically the next level supervisor. So let's see how this looks. So this one crashes, it gets restarted, it crashes immediately again or soonish again, and gets restarted again, it crashes again, gets restarted again. Now the supervisor gets fed up with it, kills itself. Because of the linking, all the other processes go away. They also get an exit signal from the supervisor. And then the whole subsystem tree gets started again. And that's kind of like, if the nesting is designed well, that very often works. So what we do, we switch it off and on again, but we do it at small units, very small system units. And then we do it in increasingly larger system units until we have to restart the whole system in the worst case. And we think a lot about our state and what we want to persist and what we can recompute. So why does that work? So back to this research from Jim Gray, and this is also from a talk. This table is from a talk from Freddie Bear. Thanks to the table. If you want to read more about like a deeper, even deeper story about how the fault tolerance works, you can watch his talk or read the blog post. The link is down here. So we basically have two kinds of bugs. One is repeatable bugs, kind of like what they called Bohr bugs before. So they're usually like, if I run my system with these inputs, it always fails. And then the other thing is transient bugs, which take a while for the system to run, and then suddenly gets in a state where things are not quite well again, which could be caused by a rare sequence of inputs, or very often by a timing coincidence, some race condition or whatever is happening, and then actually the system fails. And then we look at on the rows, we look at what kind of features the bugs are in. So either a core feature or a secondary feature. So repeatable bugs in core features are very easy to find, because if you do your job, you found them in testing already, or the type checker found it anyway. So very easy to find in testing, because you probably test all your core features, and you should actually test it with enough repeatable inputs that you found basically all the bugs. And should one occur in production from the crash logs, if you look what happens, you very easily see, oh, yeah, that's what happened. Sorry, I forgot this. Let's write another test and fix this bug. The transient bugs are very hard to actually find, because they're very hard to find in testing. I mean, there is advanced testing methods like property-based testing, which actually a lot of people in the Erlang space also like to use, because we try to crank up the reliability on in all fronts basically. But with normal testing, it's very hard to find. And if you look at secondary features, the repeatable ones would be easy to find, but they're often overlooked because we didn't write a thorough test suite for secondary features. We only have a few tests for the secondary feature or non-test. And of course, secondary features, transient bugs are even more hard to find and detect. So now look at the same table with same repeatable and transient, and look at what happens when we have a supervisor tree and actually we restart things, and which ones are fixable. So bugs handled by restart. Repeatable bugs, core features, probably not. You restart it, you get the same input again, you crash again. But they were easy to find anyway. So repeatable bugs, core features, we really need to find them with testing. But both transient bugs, basically, because they're transient, so they need time and actually a buildup of corruption in the state to actually happen. Both transient bugs no matter in what feature, are very easy handled by restart because you get rid of the corrupt state, and then you have all the time until the transient bug spills happens again, which is usually rare. That doesn't mean that you don't have to fix it, but you can actually, the system keeps running and keeps functioning, and you see in the logs that you have this one crash that happened like yesterday, and then you look at the information and try to fix the problem while your system keeps running. And even if it happens again, it fixes itself again. And that's kind of like the core of Erlang's fault tolerance. In secondary features, repeatable, sometimes actually restart happens because secondary features are used very rarely. So if you have a feature that is used like every 10 days, so you use it once, then the subsystem of the feature crashes basically, gets restarted, and then the rest of the system keeps functioning. But of course, the secondary feature was broken for the user. But if this happens again later on, then it is kind of like fixed by restarting because the rest of the system is not going down. So a citation about the frequency of these two kinds of bugs from the paper from 1985 from Jim Gray. In a measure period, 1 out of 132 software faults was a Bohr bug. The remainder were Heisen bugs. So there you see how good testing works. So basically, you don't have repeatable bugs, many of them. It's less than 1% of the bugs in a production system. So they actually looked at multiple production systems. The link for the paper is, by the way, also in the slide. They looked at lots of bugs that happen in production, and most of them were Heisen bugs, or what we now call transient bugs, and would be fixed by restarting, therefore. So yeah, that's kind of like the reasoning behind why Erlang's fault tolerance works. Yeah, there's also kind of like I already mentioned, hardware watchdogs. Basically, supervision tree gives us a fine-grained control. In embedded systems, we also have hardware watchdogs to resolve transient bugs, but it needs to restart the whole system, so it's more disruptive. But actually, there's a feature in the Erlang VM which ties nicely in with a watchdog, because there's a heartbeat service in the Erlang VM, which you can wire into a hardware watchdog. That means basically this would measure, is the Erlang runtime still alive? Because the Erlang VM is written in C, and of course it could have a bug. I mean, of course it's very thoroughly tested and used by lots of people, and it's pretty bug sparse. It's pretty robust. Because it's also used in a lot of mission critical systems, so people are very careful with it. But should it happen, then the heartbeat would stop, and the hardware watchdog would immediately know my Erlang system is corrupt. And anything that happens above that can be handled by supervision trees within the Erlang system. So that's actually a nicely interaction for embedded systems, how this works. Yeah, that's a little bit kind of like a few things picked out from the article from Fred. Basically, what do you do if you look at a system, how you design your system? So what is critical? What is not critical for the survival of the system? So you put the critical stuff in a separate pod, and the not critical on a different supervisor subtree. So if that fails, it doesn't affect the critical one, and we will see that in the example later on. What is allowed to fail, what's not, what is very bad if it fails. So you can look at different parts of the system with different eyes, basically. Also how it should boot, because the supervisor tree is also the boot order, and according to which guarantees and in what order and everything. And then so you kind of like this whole design system also makes you think a lot about how your system fails, and also the supervisor tree is doing the hot code upgrade of larger systems. So that's also a thing. And if you think about all this, about everything that's on this slide, and you use Erlang or one of the other languages like Elixir or other languages that runs on the Erlang VM, Erlang and Elixir are the main languages, you can actually build very, very robust applications which are beyond the robustness or achievable in most other systems. And actually, Ericsson did that in a project, in an old product. They built the AXD 301 ATM switch, and they built a very careful system, and it was measured by the customer, actually by BT in this case, who had a whole network of these ATM switches with 14 nodes carrying live traffic from September 2002. And they they planned 23 until 2002, and on this trial run in a live system, basically doing 30 to 40 million calls per week and node, they achieved 9 nines of availability. So this is 99.99999 and 99% of availability. So this is actually extreme. This is extremely good. So in telco, you are in business if you can achieve 5 nines of availability. 9 nines means 32 milliseconds per year not available. So this is extremely good. Of course, this required a lot of work to actually make such a reliable system, but it is the thing that gives you kind of like a way. And this is actually snapshots directly out of one slide deck that had snapshots out of another slide deck. So this is the source, the copy here, of the claim of Ericsson after their work with BT. So yeah, it gives you all the tools to build super reliable systems, and therefore I think it would be a very good choice for any system that is hard to reach when it doesn't work. Be that a mobile phone base station in the north of Sweden in the middle of winter, or be that a satellite that is actually hard to reach. It would be nice if it would fix itself. So a quick run through over kind of like what kind of like the larger Erlang system looks like. So if you start an Erlang VM, like we just did in our example, where we hacked around in the Erlang shell, you have one operating system process that runs a so-called Erlang runtime, the Erlang runtime, and the Erlang runtime runs a so-called Erlang release. A release is in the Erlang speak basically the name of a set of applications bundled together, which then get started together and actually implement one thing basically. So it's the thing that you actually run, your overall application, but it's made out of multiple Erlang applications, which you can actually start and stop independently. So they actually behave like applications. So you could actually log into the shell and then say, shut down this application, or start another one that you didn't plan for in the beginning. But the release kind of like has also the set of applications to start. And then each of these applications has its own supervision trees inside. So this slide is actually meant to be a comparison. So this was out of a talk I gave about to people actually designing a system with microservices, which is a paradigm, and to make it more understandable why Erlang is actually stronger than microservices. Because what we actually have as the smallest unit is one process. And let's call that for the sake of this argument, let's call it a picoservice. And then we have this one is managed by the Erlang supervisor tree. And then you have a nanoservice, which is the application, which is kind of like a larger thing, which can be started and stopped and also would restart the whole application. If the top supervisor fails and you configure the application that it should restart, it would restart the whole application. So let's call it a nanoservice. And that is managed by the Erlang application controller, which is kind of like a meta supervisor for applications, very similar to a supervisor. And the whole thing, the whole Erlang release running in the Erlang VM, that would be then a microservice, which you could then be managed by Kubernetes, basically. So you can actually, it would mesh nicely in a microservice architecture if you like that. But the fault tolerance that microservices give you, and also the scalability, is much inferior to what the Erlang VM can do for you, and Erlang systems can do for you, because this fine-grainedness gives you much less disruptive restarting. Because what microservice like Kubernetes starts your microservice if it fails. So it's kind of like this whole microservice architecture is taking one piece of successful things of Erlang and apply it on a very large scale, but for our taste, on too large scale. It's actually not fine-grained enough to actually be really powerful. So that's the overview. So we have picoservices, we have nanoservices. We can also work nicely with microservices, but actually very often you don't need that. So if you would live kind of like in a non-microservice world where everybody requires you to run as a Docker container somewhere in some microservice-based cloud, it would actually be more scalable to run Erlang and also more robust to run a whole Erlang system on a bare metal machine, on a raw machine, basically, because it can handle this one can handle the fault runs quite nicely, and it doesn't need another microservice layer, and it's actually more efficient because the latency between microservices is millisecond, because this is like at best, because this is different operating system processes, and the other process needs to be scheduled by the operating system, so you get millisecond latency if you bounce to and fro, and if it's on a different machine, it's larger anyway. But that would be also true for Erlang systems. And within anything, within the same Erlang service, you have nanosecond latency if you communicate, and that's 3 orders of magnitude faster. And if you hear about people complaining about problems with microservice, they always complain about latency, because these millisecond latencies add up in large microservice-based systems and then lead to very slow systems in the end. And that's actually not necessary. Let me first explain what we're doing here. So we have some example code. I will show you parts of the code first. And we actually will run this directly on hardware. So this is not running on my laptop, but it will be running on a small PCB that's on my table over there. And you will see it soon. So here we actually have 2 different supervisors. So let's assume we have a very critical system, very critical for the life of the system, which we call green blink. It's called green blink because the PCB has 2 LEDs, and it actually makes one of them blink green when everything is working. And because it's so important, we isolated it in a separate kind of like branch of the top level supervisor here. And then we have another one, which is a little bit more less critical. And at the moment, it's not buggy, but we will make it buggy. And that's running on a separate supervisor tree, and it kind of like runs on 3 instances of processes: Basil red, Basil green, and Basil blue. And what they do is basically they each wait for random times and then set the color of the other LED to red, green, or blue, overwriting what the last supervisor, the last process basically did. So randomly, these 3 processes set it to these colors. And then there's also one other process in here, which we call Sybil, which is only there to actually send a message. Whenever it is started, it sends the message next color to the green blink process, which actually makes it not blinking green anymore, but in a different color. That is that we can see from the outside whenever this whole supervisor tree actually crashes, because then the Sybil process, which is not doing anything except sitting there, and so it has a very hard time to crash unless the supervisor crashes. And then when this gets started new, it sends this message to the green blink process and makes it green blink in a different color, and that we can see that from the outside. So now I show you the board, which should be on my table. And then we switch on screen sharing again. So now you see basically this one is green blinking. That's the green blink process. And the other one at the moment it's stuck at red because it's random, and then it occasionally changes color. Now got blue, red again. So depending on how the randomness goes. So what we have here is this one where you don't see anything. That's the serial console actually connected to the board. So that's the serial console. That's where messages would actually appear, but we have an Erlang shell here, so we can do things like 1+1 here to see if it's alive. Yeah. And the node is called faulty at faulty, so it's a distributed node. So we built the whole thing here and deployed it to the SD card. Actually, I think we don't need that one. Can get rid of that one. And we actually started 2 other nodes on my laptop. So this window is on my laptop, and that is also on my laptop. And this one actually is a remote shell. So here we started this one. So this is, we gave it just a name that it has a local name. And we started a remote shell to faulty at faulty. So this is connected via the Ethernet cable. So this Ethernet cable to this board and connected to the Erlang node, and it's a distributed Erlang node, but we use it for a remote shell. So you see it's also faulty at faulty, like here, but this one is going over Ethernet, so we can do the same thing here. And the other one, this is called loader at DRAM, which is the name of my laptop, DRAM. We call it loader because we will use it to actually load remote code load, hot load changes on in the module that we will do in a moment. So for one thing, if I type nodes here, which basically tells the system like, give me all the nodes, then it actually, this one is seeing faulty at faulty, and R1 at DRAM. R1 is this remote shell. And they're all connected together basically. So we have this connected together, and then we also have our code editor here, which I need to make larger, so you can see it. And the code editor actually, here we have the green blink, and that is actually a nice example for a gen server. So that's kind of like a module starts with that, and we declare that this is the behavior gen server. So now it is actually, the compiler looks that we actually implemented all the required callbacks. And we have the only API we have, it's a start link that starts the whole thing and links to it. That's the required thing that we need to do, what the supervisor wants to call. And we export the functions here. And here, that's a record, that's a data type I didn't tell you about. That's kind of like tuples on steroids with a name. And we have a record called state here. And it has fields like timer, toggle equals false, colors. So that's a list of colors that we have. That's how it gets started, and it calls a gen server function that actually does the starting. So then it does all the bookkeeping with the supervisor and everything, and that's the initialization function. So that's automatically called. That's a callback one. You see it here to initialize your state. This is called in sequence. So you want to actually do this quickly because these are all kind of like in sequence. And here we only send ourselves basically. We set up a timer to send ourselves a message every 500 milliseconds. This is the message blink to ourselves, and then we put the reference to this timer just to be clean here and into the timer, because we will keep this timer handling. So then there's calls. You can do gen server call. That would be kind of like synchronous callbacks, which then end up with a handle call, but we don't have any. So this is an NP implementation, so we ignore everything and just return the state again. And the reply is okay. Whatever you tell it, it says okay. And handle cast, actually, that's an asynchronous call, basically. And it actually listens to next color. And that's the one that the Cybele thing will send it. And then it actually gets the colors here. It splits up the first color. It appends it to the end. And it also, at the next blink, basically, at the next update, it will look at the color. So whenever we get a blink message, which is the timer, we look at the first element in the list here. So we see we pattern match this out in the state, and we actually pattern match the fields of the record and the parts of the list in one thing. So this is already happening, giving me the first in the list of the colors, and we set the letter number 1 to this color. And then off in the other blink, basically. Every second time when toggle is true, when toggle is true, we actually switch it off, and toggle is false, we switch it on, and we toggle the toggle. That's all. And then there's a few other things that we don't need. Handle info is basically handling arbitrary messages like the one of a timer. So that's actually a very small module where you can actually see how this looks. Let's look at the top level supervisor. So the top level supervisor only has basically the green blink process. So looking at the graph here, green blink, that's the faulty supervisor. It has green blink and it has another supervisor, the basal supervisor, underneath it, basically, as a secondary supervisor. Oh, this is per buffer. You can't read it. I'm sorry. I think I need to change the default font. Set default font to lots of points. 18. Let's try 18. Okay. So now everything is a bit larger and more readable, but my window got too large now. So I need to shrink it a bit to a useful size. And let's look at another supervisor for an example. So here we basically, the supervisor actually only has a configuration. So in the init function, it returns this the configuration, and we have the supervisor strategy. This is a 1-for-1. That's the restart intensity and the restart period. So if it restarts more than 10 times in a period of 10 seconds, it actually kills itself. So since we don't want it too often, we set it pretty high, and then it just returns the data structure. So, sorry. And if you look at the basal supervisor, there we see we have multiple children. We have Sybil, that's what it starts. Restart permanent, so you can also say what it should do when it fails. You can say this is transient, so run it once and only restart it when it doesn't stop normally, or there's all kinds of configuration things that are not important here. So now, for now, we restart everything permanent, and we basically, so the basal supervisor actually always calls the basal model start link, but with a different argument, red, green, and blue. So we get, basically of this one module, we get 3 processes running the code of this module. That means that if we upgrade it, we upgrade basically all 3 processes code. So let's look at the basal code, because that's the one we will be messing around with. The basal code has, this is a bit of contrived example. It initializes nothing important, timer reference color, interval equals 7 in the beginning. And whenever basically a timeout happens, so that's this handle info here. Whenever the timeout happens, when we get the set color timeout, then what we do is basically get the timer, we get the color from the state, we get the interval from the state, then we set the color to the one that we decided last time. So last time this was running, we set the color. It's a weird contrived example. And then we start the timer again, and we actually round it to this interval from that last time, and we divide 20,000 milliseconds by the interval that we actually calculate, and we send it to self set color. And then we calculate a new interval by a random number between 0 and 100 times the old interval for whatever reasons, complicated things. And then we take the remainder of it, also 100. So what we get here is the number from 0 to 99. And because we want to divide by this interval, the next time we are called, we actually add +1, so it's 1 to 100. And you can imagine what I would be doing now, because so this is working nicely. So it has no bug, basically. Well, no known bug. I hope you can see that. I get it. So it still blinks, the green blink is going on, and the basal sets random colors. So what we do now is we remove this +1 here. Thereby introducing the bug that interval can now be 0, and we might be dividing by 0 here. But because it's based on the random number that we just calculated, it will run every time, basically every 100 times this is run, basically it will crash. And what we expect is basically then, well, we expect that it will be restarted. So the blinking, we kind of like continue, maybe a little bit in a different frequency or whatever because of the restarts, but that's all. So now I need to kind of like work one-handedly, because what we do here we are in our loader thing. Because currently I only changed the source code. So what I do here, this is in the same directory. I compile the Bazel module. So now we have a newly compiled Bazel module loaded into this node. And then actually what I do is I do net load Bazel, which does the loaded module gets then distributed on all other nodes in the distributed network, including this board, and it net loads it. And because the Gen server is hot code upgrade friendly, you can see here's even a code change here. So even if your state formatting changes, you can here start from old state to new state basically. But we didn't change the state, so it is actually it will just work. It will call the new code immediately. But when I do this, I change the code in the board. So everything is still fine. We are blinking. Green blink is going on. And actually, I should have a crash, but it's probably pretty rare now, because it needs to trigger the 0 first. But I wanted a rare crash, so we can actually wait for it and then look at the crash dump. Oh, my arm is getting tired. This is getting boring. Let's reduce the number. I hope I'm not overdoing it. Nope. Typo. Oh, did I even save the bug? Oh no, I didn't save. That's the thing. So let's put 20,000 here again and save it and then compile it again. And then while I show you the board again in the camera, do the net load. And then we expect crashes to be happening eventually here. I hope. Yeah, there we have our crash. So, and you see the crash dump contains a lot of information. So if you get this in your logs, you can actually debug this very easily because it tells us where it happened. It happened. Oh, we need to stop this. The serial line is a little bit annoying because it keeps crashing now. So it happened in handle info in line 31. It tells me everything where it actually happened. It tells me all the context and actually what happened. And the reason is bad arithmetic in line 31, which happens to be the line there where we did the division. Okay, so far, the green one is still blinking nicely. So green blink is not affected because this only occasionally crashes. And it didn't go beyond the crash frequency of the actual supervisor. I'm not sure how much I need to put. I forgot the number. Let's try 5,000. Was this 5,000 or 500? Well, let's just try it out. Compile, net load. So now you see it's much more frequent. It keeps crashing. And then we should see whenever it crashes too often, then the green blink should actually not blink green anymore, but in a different color. Now it does a red blink. So actually now the whole supervisor crashed and it actually sent the message to the other one. So now it does yellow. So that's the thing I wanted to show. So that was our demo of the supervisor tree and how it worked. And we actually did this on a board. And this board I actually mentioned is running the Erlang VM directly on hardware. And what we did here is years ago, we combined the Erlang VM with the RTEMS executive, which is kind of like not real an operating system because it's only a library, which lets you boot into the whole system. And what we use from this library is like we use the threads for the supervisor threads. So not the supervisors, the scheduler threads. And we use it for file IO, and we use the TCP stack of RTEMS. And we tied this together and we call this a GRISP stack. And so especially in the round of flight software developers, RTEMS is well known. It's actually it's coming from aerospace, and it is actually NASA and ESA space approved. and is about as old as Erlang, funnily, and running in several space probes. So now we combine something very robust, or a system to build very robust systems with a very robust base system, and run that direct in hardware. So how does it look? So traditional architecture, you have your Erlang VM, the red box on the left, and your Erlang application or your release running in the Erlang VM, and then you have other software, and everything runs on operating system, and then the operating system takes care of the hardware. So let's say this is Linux or whatever. And whenever I want to talk to the hardware, I need actually a driver in the operating system to map this hardware to some system calls, and then I need to usually have a driver to talk to the system calls to actually talk to some real hardware for embedded systems. So this is a bit annoying. And also the operating system, if it's not hard real time, it kind of like messes with our real timeness all the time. And if we run it like in the Crisp system, like everything together, in bound together, like the Artemis library with the Erlang VM bound together, other software is just linked together, and we put the whole thing into hardware, we basically have nothing in between us and the hardware. So the Erlang VM, when it calls out to C level, we can actually set the bit of the hardware and have very low latency towards the hardware. And also there's one learning, unfortunately I don't have measurements about that. I should actually put a PhD student or a master student, no, it's more master student thing, on measuring how the real-timeness of Erlang changes when you run it on a hard real-time operating system. Because the observation is it gets much harder, the soft real-time, because one of the causes for kind of like jitter is the operating system, actually. So that's the software stack, and what we do here is we actually can build mixed critical systems. So we have Erlang soft real-time stuff with our space partitioning, and then we can also run C and C++ code. Let's say a traditional flight software stack, for example, or whatever. In most systems, a very small kernel of code, which needs really fast hard real-time, that we run in C on a higher priority than the Erlang system. And then we have time partitioning between that, because that always runs, and the Erlang system can't mess with it. But very often you have like a little bit more requirements, especially when you have a TCP stack, because the TCP stack is kind of like a weird thing to place in a real-time system. So you kind of like, you don't want it at a too high priority, because then if the network gets flooded, it actually disrupts your real-timeness. So if a lot of traffic is going on. But if you have it at the lowest priority, then if you have a web server running at a lower priority than the TCP stack, that's also a very weird situation. So what we actually want is, we want maybe something like that. And we actually did an experimental implementation of that. So we created a second set of schedulers threads within the same Erlang runtime, and we run one set basically on a higher higher real time, which I call the harder real time here. And we put the network stack above that one and a lower priority, so I can't disrupt that mission critical things. And then the web browser or web clients or web server is running on an even lower priority. So we actually did some preliminary work on that. And in the end, we actually have a plan to do hard real-time Erlang processes. Not like nanosecond hard real-time, but reliable hard real-time, staying in a pure functional high-level language with garbage collection. But this is a separate talk that I already gave at conferences, so you can actually find it somewhere. So around the whole thing, we actually build a nice tool chain. So kind of like we have the cross-building tool chain from Artemis, we have Artemis itself, and we have the Erlang VM source code, like the current source code of the Erlang VM that we're actually using. And what we need to do is we need to cross-build the Erlang VM into an image, and then we actually add the actual Erlang code, the compiled Erlang code. And because we don't change the Erlang VM so often, and if you don't touch C code in the Erlang application, so if you don't have like what we call a NIF, a native implemented function that actually calls out into C, which we touch, so we only use the bundled C code, then we can actually use pre-built versions of the Erlang VM, because we cross-build it once and it just downloads it. It sees, oh, nothing changed in the C code level, I just use the pre-built stuff, and that is all built into the. So Reba is the main build tool for Erlang, and also there's Mix, another build tool for Elixir, and we actually build plugins for both build tools that actually take care of all of that. So you don't have to do anything, because the main thing is that we want to reduce the friction to actually use embedded or build reliable embedded systems as much as possible. The board that I waved in the camera, that's an evaluation board, which we built that we actually can control the hardware and can actually provide the best possible user experience, because we control everything, and it's meant to be getting started quickly. The black plugs above there are PMOD connectors. The PMOD connectors are PMODs are kind of like little modules which are quasi standardized by a company called Digiland. And they also sell a couple of hundred, well, I think 150 or something different PMODs with sensors and actuators. And that's usually around an SPI or I2C interface. And there's lots of other I/O there. There's an Ethernet there, an SD card slot. It has also a built-in eMMC here. So you actually have two kind of like disks. One where you can program something and do remote code upgrade, and one where you can actually plug in, so you could put data in there. It has a Wi-Fi antenna here and a Wi-Fi subsystem. It has one wire, a plug for a battery pack, and lots of other stuff. We use the same board to prototype our own stuff. So for example, we used our own evaluation board, and we made this custom PMODs, because that's a much cheaper hardware project. Because kind of like designing a new PMOD costs about 5K. For industrial I/O, and we also used the RFID antenna here, PMOD that we did here, antenna plus controller, and we used that to kind of like prototype this thing, and we had the software running before we actually started the hardware design. I don't have a slide for that. For this thing, which is an industrial controller system that runs the same Erlang thing directly on hardware, and is meant to control conveyor belts in manufacturing, because that's one of our vertical use cases we use the technology in. We have a lot of available technologies in the Erlang domain, many of which we built ourselves. We have a complete OPCOA stack in Pure Erlang, which is an interesting SCADA and fieldbus protocol, which kind of like takes over the world at the moment and replaces all other SCADA and fieldbus protocols. It has a few pretty good properties. I don't have time to get into that. Look it up. It's a nice protocol, but a little bit complicated. But we built a complete stack in Pure Erlang, so it integrates very deeply with our system. We also built an IEC 64099, which is the standard which it is defined in PLC programming language, a distributed version of it, because in manufacturing we want PLC programmers to be able to use our systems. We have Ethernet TSN code written in Erlang, a control plane. There's a ROS2 implementation in Pure Erlang, done by a master student with everything. So it's kind of like it doesn't use any of the existing libraries. It's built from scratch in Erlang in a master thesis project. So there you see the productivity also, what you can do. If you take a very smart master thesis student and let them run with a year, they can build a ROS2 clone, basically, with Pure Erlang and with hot code upgrade, because he demoed that in his thing, and he also gave a talk. And as a matter of fact, he works for us now. So we actually have the developer of Rosie also on board. And that lets us interface with a lot of ROS2 systems. We have lots of secure boot, secure element is on every of our devices, and that ties into that. We made an orchestrator that actually orchestrates Erlang nodes in a secure way, worldwide, basically. And in a legacy product, I built all automotive protocols in Erlang. I said that already. Currently, we are building Grisp Nano, which will be a much smaller evaluation board, which is supposed to be running off temperature gradient energy harvesting, and that should be the most low-power board that runs the full Erlang runtime. There's a Erlang runtime called Atom VM, which runs a subset of the Erlang VM, which runs on even smaller hardware. But since we want to migrate our code around and actually place it wherever it needs to be, we are building a thing that actually runs very small in the full Erlang runtime. So this will be on ARM Cortex M33, 160 megahertz, 32 megabyte external memory, which is plenty still. So we can squeeze it smaller if we need to. And the radio we are using, or actually the network we're using for that is ultra-wideband, 802.15.4, high bandwidth with low power. We need low power because of the energy harvesting requirement. We have only milliwatts. And it also gives you time of flight measurement because it has basically wide bandwidth and has a radar pattern as a preamble. So you can actually position nodes in meters, and it goes like 30 meters. It's like in personal area network space. But that's just one example for a small board we can build. And what we're also working on, we built Crisp.io. That's a cloud edge IoT distributed compute platform, where the new thing is that we place the computation where it needs to be according to user specification. So not like it's done today that you write your code in one programming language for one type of node, like for the IoT node, and then another programming language for a gateway, and then another programming language for the cloud maybe, and think of the same thing in space applications on ground station, cloud, on the satellite maybe, or on a subsystem of the satellite. And we want to get away from that. We want people to actually specify a whole distributed system and specify their requirements for latency and everything. And as a user intent, you also describe your network of distributed heterogeneous nodes, which are all different and different properties, and we want to automatically map the computation where it needs to be. And for anything that's based on the Erlang VM, that means like in Erlang, Elixir, or also in IEC 64099, I don't know why they don't give the programming languages better names. They all can do this in a very fine-grained way into very small IoT nodes, but we also will integrate containerized things. Like if you have a containerized machine learning thing in Python, we can also place that on the node with the GPU, or maybe preferably on the node with the cheap GPU and not on the expensive cloud GPU. Well, that was it. Well, 2 hours, okay. I only overstepped half an hour, sorry about that. Well, people that watch the video can watch it in twice the speed, maybe. Yeah, so we really hope to get our technology into orbit somehow. And that's why I was talking in front of flights of the workshops, and I will show up at space conferences until I achieve this goal or actually pay for my own CubeSat eventually. Because I think this is really a good technology to be used in space applications.